Hello and welcome. I'm Stephen Proud, and in this video we're going to analyse a famous mathematical problem called the Monty Hall problem. The Monty Hall problem is based on a game show that ran in the United States from the 1960s onwards called Let's Make a Deal. In one of the games within this game show, contestants were presented with 3 doors and offered the choice of one of those 3 doors. Now, behind 2 of those doors were pictures of goats, indicating that the contestant hadn't won a prize. But behind the 3rd door was a sports car, which represented the grand prize for the game show. Now, the way this final game worked was something along these lines. The contestant doesn't know behind which door the sports car lies, but the presenter, Monty Hall, does know. So the contestant is given the choice of any one of the 3 doors. So let's suppose that they choose this door. The presenter then reveals one of the pictures of goats behind one of the unchosen doors. The contestant is then given a choice. The contestant could either stick with their original choice, in this case the red door, or they could choose to switch to the other unopened door. Now the question is, what would be an optimal strategy for the contestant, and for different strategies, what would be the probability of winning the sports car? So in this case, should the contestant stick with their original door, or should they switch to the unopened door? Now we're going to try and analyse 2 possible strategies. The first strategy that we'll consider is where the contestant always sticks with the original door chosen, and the second strategy is always to switch to the unopened door, and we'll try and calculate the probability of winning based on each of these strategies. So let's begin with the first strategy, always sticking with the original door chosen. And probably the easiest way of analysing this is to think about how the game works without the doors in place. So here we have a possible arrangement of the pictures of goats and the sports car. So let's suppose that the contestant chooses the first door. Well, what will the game show host do? Well, the game show host will reveal the second door to reveal a picture of a goat. And if the contestant's strategy is always to stick with the original door, that means the contestant will win the picture of the goat, so they don't win their star prize. Similarly, if the contestant chooses the second door, that's another door with a goat behind it, Monty Hall, as the game show host, will reveal the first door with a picture of a goat behind it. Since the contestant is always sticking with their original choice, they win the picture of the goat, they don't win the star prize. The only case where the contestant wins the star prize is where they initially choose the door behind which the sports car lies. Monty Hall could open either the first or the second door. So let's suppose that he opens the first door, and as the contestant is always sticking with their original choice, they win the car. So we can see that whenever the contestant originally chooses the picture of the goat, they win the picture of the goat. Whenever they originally pick the car, they win the car. So we've just seen that if you always stick with your original door, you're always going to win the prize that you've originally chosen. You know that a third of the time when you're randomly choosing across the doors, you'll choose the door with the car behind it. So because you're always winning the prize that you've originally chosen, the probability of winning the car with this strategy is 1/3. Now let's consider a second strategy. The second strategy is where you always switch to one of the unopened doors. So let's do the same analysis with the doors open. If you choose the first door with a picture of a goat behind it, then Monty Hall will open the second door. You switch to the only other door that isn't open, which is the third door, and you win the car. Similarly, if you'd originally chosen the second door, Monty Hall would open the first door, you would switch to the third door, and you'd win the car. Finally, if you'd originally chosen the car, then Monty Hall could open either the first or the second door, and you'd switch to the unopened door and you would win the picture of the goat. So with this strategy, whenever you initially choose the picture of a goat, you win a car. Whenever you initially pick a car, you get the picture of a goat. So we can see that 2/3 of the time we would pick a picture of a goat. So in this strategy, 2/3 of the time you would end up winning the car. So straight away we can see that this strategy looks superior to the strategy of always sticking with the original door. Now let's try and analyze this mathematically. So let's define two random variables. Let's define your initial choice as x and the prize that the contestant wins, y. So we can write down probabilities relating to the initial choice straight away. The probability of picking a picture of a goat is 2/3. The probability of picking a car initially is 1/3. If you're always switching, we can also write down some conditional probabilities relating to the prize that's won. So for instance, when the initial choice is a goat, so when x is a goat, we know that the contestant will always win the car. So the probability that the prize is a car, given that the initial choice was a picture of a goat, is going to be 1. Similarly, the probability of winning the car when the initial choice was a car is 0. The probability of winning the picture of the goat when the initial choice was the picture of a goat is 0. And the probability of winning the picture of the goat, given that the initial choice was a car, that's also going to be 1. Now what we want to calculate is, based on this strategy, what is the probability of winning a car? In other words, what is the probability that y is equal to a car? Now in order to calculate this, we're going to need to appeal to the law of total probability. That is, we're going to need to add together all of the joint probabilities where the prize is a car. So in other words, we need to know the probability that the prize is a car and the initial choice was a car, and we need to add that to the probability that the prize is a car and the initial choice is a goat. Now, to calculate these joint probabilities, we're going to need to appeal to another rule, which is the chain rule of probability. That tells us that the probability of, for instance, x being equal to some outcome little x and y being equal to some outcome little y is equal to the marginal probability that x is equal to that outcome little x multiplied by the conditional probability that y is equal to little y given that x is equal to little x, or the marginal probability that y is equal to little y multiplied by the conditional probability that x is equal to little x given that y is equal to little y. Now let's apply that to each of these joint probabilities in turn. So the first term, the probability that the prize is a car and the initial choice was a car, we can calculate this by multiplying together the probability that the initial choice was a car by the conditional probability that the prize is a car given that the initial choice is a car. Now we already know that that conditional probability is equal to 0. So the joint probability that the prize is a car and the initial choice is a car in this strategy is going to be 0. Similarly, the probability that the prize is a car and the initial choice is a goat is going to be equal to the probability that the initial choice is a goat multiplied by the conditional probability that the prize is a car given that the initial choice is a goat. We know the probability that the initial choice was a goat, that's 2/3. We know the probability of winning the car given that the initial choice was a goat is 1, so that joint probability is going to be equal to 2/3. So we can use this to calculate the probability of winning a car as going to be equal to 0 plus 2/3, which is equal to 2/3. So we've just shown that if our strategy is to always switch, then the probability of winning the car is going to be equal to 2/3. I'm going to leave this as an exercise for you to do, but you can also show that if your strategy is always to stick with the original choice, the probability of winning is 1/3. Now there is a third strategy that we have not discussed, and that is to randomly choose between either your original door or the other door that has not been opened. It's possible to show that if you follow this strategy, the probability of winning the car is 1/2. So that's still better than when you always stick with the original door, but it's less good than when you always switch to the other unopened door. In this video, we've analysed a very famous mathematical problem known as the Monty Hall problem. When we've solved this analytically, we've used two key rules in probability. The first is the law of total probability, and the second is the chain rule of probability. Now, most people, when they look at this problem intuitively, will get the wrong answer. Most people will assume that the probability of winning is 1/2, irrespective of the strategy that's used. We've shown that the strategy very much matters, and the optimal strategy in this case is always to switch. And that's because the game show host actually provides us with new information when they open one of the doors to reveal the picture of the goat.